Okay, so a few friction problems here. First of all, let's imagine that you push something across the floor and it slides for a while and eventually stops. The question is, what's the best force diagram? Well, if you think about that for a moment, this is the best choice because there's only three forces. There's a normal force, there's the weight, and there's also the force of friction. Now, you may ask, well, how can it be moving to the right if the force is to the left? And the answer there is the motion is due to a previously applied force that is no longer present. So that previously applied force is no longer present. That's what made it move, got it up to a certain speed. Now it's been released. Because of friction, it's going to start slowing down immediately, but it's going to take a certain amount of time for it to come to rest. Now, for that cart then, let's find an expression for the acceleration. So the forces that act on it were normal force, weight, and friction. That's just from the force diagram above. And now let's apply Newton's second law, which just says net force is ma. But we're going to apply net force is ma in both the vertical direction, up and down, and also in the horizontal direction, left and right. Now up and down, there's two forces. There is the normal force and the weight. But because it doesn't move, there's no motion up and down. No motion tells us constant speed, tells us zero acceleration. And no acceleration means zero net force, means those two forces, the normal force and the weight, have to be balanced with each other. Or another way to put it, normal force minus weight equals zero. So we have balanced vertical forces in the y direction. The normal force just equals the weight. Now that's useful because as soon as you know the normal force, you can calculate the force of friction. And in the horizontal direction, the net unbalanced force, the only force, in fact, is friction, which acts to the left. So that tells us the acceleration will be to the left as well. But we know that friction depends on two things. It depends on the surfaces in contact and the amount of squeezing. We've just shown that the normal force is the same as the weight by the vertical force analysis. So our force equation then says this expression for friction must equal ma. We can cancel an m, and we get an expression for the acceleration. So this problem introduces the idea that we're going to analyze force components just like we analyzed velocity components in the projectile motion problem. Here's another example. This is actually two problems here in one. We're pulling a block here just with a force of 20 newtons, and then we come along and we push down on it a little bit more. So this is two questions in one. So in each case, we want to draw the force diagram. Well, there's a weight force, mg. There's the surface pushing up. That's called normal force. We're pulling the block to the right. That's like an applied force, F. And then there's going to be a force of friction that resists that sliding. Now, in the second case where we're pushing downwards, we expect that the normal force is going to get bigger, and therefore the friction force is going to get bigger. So we'll draw those on accordingly. Alright, so for each block, let's start with this one. Let's analyze the vertical forces. So I'll draw a little T-chart here. So vertical, horizontal. Okay, in the vertical direction, again, net force equals ma, but because it doesn't move up or down, the acceleration is zero. So the net force, which would be the difference between Fn and g, because they're opposite to each other, is zero. Or another way to put it, we have balanced forces. The normal force just equals the weight. Now, for a 10 kilogram object, that's 10 times 9.8 is 98 newtons. Now, in the horizontal direction, well, I suppose we better calculate friction first to see which one's bigger. It's mu times the normal force. The mu value of the two surfaces is given as 0.12, and that works out to be 11.76 newtons of friction. So clearly that's smaller than the applied 20 Newton force, so we know there is a net force. We know it's to the right because the applied force wins, and that net force will equal ma. So we can simply substitute in the 20 newtons of applied force. Then we can subtract the 11.76 newtons of friction, put in the mass of 10 kilograms, divide both sides by 10, and then get the acceleration. So this is 8.24 divided by 10. The acceleration works out to be 0.824 meters per second squared. So this very slight modification of this problem now, where we just add this extra downwards force, how does that affect our analysis? Well, it's still true, of course, that in the vertical direction, the net force is ma. In fact, that's always true. We're going to be a little bit more careful here, though, because now there are three vertical forces. There's upwards normal force, Fn. Then I guess we have to call this something. This we're calling F. Maybe we'll just call this one Fy because it's in the y direction. Now it's downwards. So we'll subtract Fy and mg. There's three forces in the vertical direction. Now there's still no motion, right? It doesn't move up or down at all. It's just sitting there. That's going right and left, not up and down. So there's no motion in the y direction, in the vertical direction. So that means that the y acceleration is 0. And if you make that whole term 0, you see that we arrive at balanced forces up and down. Another way to write that would just be to say, you could just write straight to the equation that up and down forces have to be the same. They must be canceling each other out. So the upwards force is the normal force. Then the two downwards forces are, first of all, the y force, and then second of all, the weight. Now, clearly, mathematically, that's the same as what you would get here after you made this side 0. It's just a slightly different way of reasoning, I suppose. So we can work out what the normal force is. It's going to be 15 plus the 98 newtons of weight, because it's the same 10 g's there. And so that's 113 newtons. So now, when we calculate the friction depends on the mu and on the squeezing force. It's still the 0.12 mu, but now we have 113 newtons of normal force. So let's just quickly work that out. 113 times 0.12, that's 13.56 newtons of friction. And so that's still less than the applied force, so we do still have a net unbalanced force. It'll be the applied force minus the opposite and smaller friction that equals ma. Substitute in the forces and the mass, and we solve for the acceleration. This is 6.44, divide by 10, it's 0.644 meters per second squared of acceleration. So, again, we see the y forces and the x forces, or the horizontal and vertical forces, analyzed separately. We see Newton's second law applied to both those directions. This problem, a little bit more complicated because we had three vertical forces that balance each other out. In both cases, friction is proportional to the normal force. Friction is mu Fn. In both cases, the net horizontal force produced an acceleration.